Hello, Math 133 students. I received a request for help with this question, which is 4.2.21 in the homework for MyStatLab. Okay, so as per usual, I'm not actually going to do this question. I'm going to, I'll click on View an Example here. So under Question Help, I'm going to view an example, and I'll work through the example, which will be very similar. All right, so the following data represent the speed at which a ball was hit in miles per hour and the distance it traveled in feet for a random sample of home runs in a Major League Baseball game in 2018. Complete parts A through F. All right, so first thing they want us to do is find the least squares regression line, in other words, the line of best fit, the linear regression line. And they're going to show you how to do it by hand. You can ignore all that garbage. We don't care. We're just going to click here to view the data. And we have the data right here. So we're going to click here and we have a choice. We can open it in StatCrunch, we can copy it to a clipboard, or we can open it in Excel. So if you copy to a clipboard, then you hit Control C, and then you can go to, I don't know, make a new Google Sheet, and you can paste that data in. So that's one option. So here I am, and I can hit Control V and paste it in. All right, so that's an option. Oops, I just put Control V twice. Okay, so I could work off of it that way and say this is 4.2.21. There we go. Sorry, just have to name it for myself. And then I can take it from here, and then of course we don't find our regression line in here. We find it in StatCrunch. So I can go to statcrunch.com, I can log in, and then I can paste that data in there. There we go. I can click Open StatCrunch. And then I can paste the data from this Google spreadsheet, so I can copy and paste it into StatCrunch. Now, what's the difference between that and just opening it in StatCrunch in the first place? No difference. I mean, it's up to you. So how you want to do it. So you can go there. Or if I had gone, oh, sorry, I lost my window. There it is. So let me close this and show you. If I click on Open in StatCrunch, then it just opens a new window right here, and it's loading in StatCrunch. The one issue I've had with this is it's a nested window, and it sometimes isn't quite happy with me. So it sometimes gets a little fluky. That's why I prefer to open it in a spreadsheet program and then paste it in. It gets a little wonky with me sometimes inside this window, because you can see this is a smaller window. It's kind of nested inside. It's not one of the tabs of my browser, and I can't really make it one of the tabs. And so that's kind of showing you it's a nested window. And I've had some issues with that in the past, not always. So your choice. Either open it in StatCrunch right away or copy and paste it into, like a spreadsheet program and then paste it into StatCrunch from there. All right, so now we have StatCrunch, and that's lovely. So we can go to Stat, Regression, Simple Linear. All right, so we want to know if the speed impacts the distance. So speed is our x variable, and distance is our y variable. And remember, we can ignore all that other junk. So we just click Compute, and there we have it. So according to this, the equation of the line is right there. Distance is, of course, your y variable. That's equal to negative 67.684 plus 4.603 times x. There we have it. All right, so if I go here and I just type this out. So when it wants the equation, the least squares regression equation, or model, same difference. That to me is that. Another way to write it would be, here, let me insert an equation here. There we go. So we could say y equals, let's see, y equals negative 67.684 plus 4.603x. Okay, that's writing it as stats people write it. If you want to write it as an algebra person writes it, you would keep the same numbers but reverse the order. So you'd say 4.603 minus 67, or 4.603x minus 67.684, right there. That's the equation of the line, one of those two. So now if I go back to the example, you can see, let's see, right there. They show all this by hand stuff. We don't have to worry about that. There we go. So they have 4.602 and 67.626. There's a slight rounding error there. I'm not worried about it because it'll be marked correct being within the thousandth decimal place of this. So we'll be fine. So yeah, we're just a tiny bit off. Actually, it's that the answer in there is a tiny bit off, and that's because they're doing it by hand. So, but that's okay. It should mark you correct. Let me know if it doesn't. If it doesn't, send it to me. But it should mark you correct because there's a tolerance on these. So it should take slightly different answers from what they type in. All right. So now we want to interpret the slope and the y-intercept if appropriate. Okay. So the slope is the number that's always multiplied by the x. Right? So it's always the number that's with the x variable. And to interpret it, we have a script in the notes, and we would use that, right? Oops, so I'm going to go back here. I just realized I should zoom in so you can see a little bit better. All right, so there's the equation written that way or that way or that way. Now we want to interpret the slope. So the slope is the 4.603. It's the number that is multiplied by the x. So now to interpret that slope, we would say, okay, now remember what our x variable is. Our x variable is speed in miles per hour. So for every, on average, there, I just thought I'd add in a little piece. If the speed with which a baseball, because I think this was baseball, is hit increases by 1 mile per hour, mph, because that was the unit, then we expect the distance to increase because it's a positive number. So to increase by 4.603 feet or something to that effect. Right, so that's the script. It's in the text, it's in the notes, excuse me, on section 4.2. So on average, if x increases by 1, it's always x goes up by 1 because this is really 4.603 divided by 1, right? So, I mean, any number is divided by 1. So if x goes up by 1, y, in this case, is going to increase because this is positive by 4.603. And then, of course, because it's a math class, we have to attach the units for each of those. Okay, the y-intercept does not make sense. Let me kind of say why. So y-intercept here. Remember that the y-intercept is a point. So it's always 0, comma, and then the constant that's sitting there by itself. So in this case, it's 0, comma, negative 67 point, yada, yada, yada. Okay, so why does that make no sense? Well, let's think about this. So this is the miles per hour with which the baseball is hit and the distance it travels. So how exactly do you hit a baseball at 0 miles per hour? You don't, right? So, I mean, I guess you could argue a punt, but then it's going backwards 67 feet. Like, it doesn't make any sense, right? So the interpretation is that this will not make sense in the context of the situation. Even a punt or a bunt, you're still doing something anyway. All right, so that's all there is for that. Right? And you're not going back negative 67 feet either. So that's another. I mean, you could also argue it's well outside the scope of the model. Even if you want to argue that a bunt, which is when they just grab the bat, they kind of were swinging it and then they grab it and kind of hold it out. Even if you want to argue that's 0 miles per hour, the problem is that we didn't have any data remotely close to that in our data set. I mean, we were striking the ball at 100 and some miles per hour for most of these, 99.4 down there at the bottom. So there's no way that that was what was going on. We have no data that's remotely close to a bunt. All right, which is a technical baseball term. Not that I know much about baseball. All right, next part. Let's see here. So then predict the mean distance of all home runs hit at 105 miles per hour. So in other words, you take 105 miles per hour and you substitute it into your equation and find the value, right? So let's see here. Okay. So predict mean distance at 105 mile per hour, right? So if you have a swing at 105 miles per hour, what's the distance? Well, you can take your equation, either one, it doesn't really make any difference. Maybe you're more comfortable with the one on the right because that's more algebra. So I'll just kind of bring it down here. So 105 miles per hour is a speed. So you're going to put it in for x. So where there was an x, you're going to put 105. And then you grab a calculator. Me personally, I'll grab Desmos. Right? It's a free calculator. It's also an app you can get on your phone. And then I will just type that in. So 4.603 times 105 minus 67 point. Here we go. 4.603 times 105 minus 67 point. I can't remember what it was. 684. There we go. 415.631. So we predict it would be 400. No, I can't remember it. 415.631. And it'd be feet, of course. Right? And it's not really exact, so I shouldn't put an equal sign in there. It's really approximate. I mean, everything we're doing is rounded based off of this equation up here, which technically is approximate in its own right, but we won't deal with that. All right, so we would guess 415.631 feet. So let me go back and double check my answer as I continue on to get the next question. So don't worry about, see, 415.6 feet right there. Lovely. So now, if a ball was hit with a speed of 105 miles per hour, predict how far it will travel. Well, we just did that. That's what the mean is. So when you find the mean, you're kind of finding that, right? So we did answer that question for D. So D is the same question. The mean distance traveled is the same as the prediction, right? In other words, if you look at the line in your regression equation, that line right there is the mean. It's the average distance, right? It's the average combination of speed and distance. So the answers to C and D are the same. So I'm just going to say D, same as part C. Smiley face. Okay, now E. So then they give us a person. All right, so Christian Yelich hit a home run at 398 feet. The speed at which he hit the ball was 106.2. So did this ball travel further than you would have expected? All right, so 106.2 miles per hour. I know it might seem like you should put 398 in for Y, but no. What you're going to do is put 106.2 in for X and then see if it's farther along than 398 or not. And here, you guys are more comfortable with the algebra version. So let me go right here. Okay, so here's the equation of the line. And where there was an X, we're going to put in 106.2. And of course, we're going to make, Desmos do that. Okay, so we still have it. It's sitting right here. So you can just go in that equation and retype it as 106.2, and you get 421.15. Okay, so 421.15 feet. So that's how far we expected it to travel. So the line, the least squares regression line, is expected, right? It's the prediction that we make. So we made a prediction, or we make a prediction of 421 feet. But in actuality, real life, the ball traveled 398 feet. So then the question is, did this ball travel farther than you predicted? And the answer is no, it actually traveled less far, right? We had predicted 421 feet, and it only traveled 398 feet. And of course, if the problem's different for your particular problem, they can change these numbers. So you should not take my word for it. When you do this problem, double check, right? Because if it traveled farther in real life than you expected, then that would be one thing, right? So in our case, but again, double check for your own case, the ball traveled not as far as we predicted. Right? We predicted 421 and it only traveled 398. But again, that can change from problem to problem. I mean, as can everything in this. All right, last bit, I believe is a would you feel comfortable? Yeah, would you feel comfortable using the least squares regression line to predict the distance for home runs where the speed of the ball was 122 miles per hour? And the answer is no. Let me show you why. Okay, so here, let me bold this and make it size 19 so you can see. Okay, the answer is no. And let me go back to the data set. If you look at our data set, the lowest speed we had was 99.4 miles per hour, and the highest speed we have is 107.9. No, it's got to be one that's bigger than that. 110, 110.14. That's nowhere near 122. So we don't have any data that's remotely close to 122. So the answer is no, it's outside the scope of the model. And again, I can't guarantee that will be the answer for your particular problem, but you want to go look at your data set. So our data set had no speeds remotely close to 122 miles per hour. So an X value that high is far outside the scope of the model. Right? You only want to make predictions that are very close to the data set you actually have. Another reason, by the way, that the Y-intercept doesn't make any kind of sense in this problem, right? It just occurred to me, I thought this was the speed at which the bat was hitting, but it could be, yeah, speed at which a ball was hit, right? But anyway, we don't have anything remotely close to 122. So that would be here, no, period. Sorry, that's the beginning of the next sentence. So I would not feel comfortable because that's far outside the scope of the model, right? An X value of 122 is far outside the scope of our model. There we go. All right, I hope that helps.